Good afternoon, everyone. I hope you still have enough energy for this talk. It should be simple enough. So I am Luc Bourlier. I'm a software engineer at Lightband. Lightband is a company behind Scala, Akka, and Play. In Lightband, I'm a part of the fast data team, and we are working mostly on the interaction between our products and the other big data and fast data tools. So in this presentation, I will start by just make sure that we all understand the basic concept of what I want to speak about. Spark streaming and what are our reactive applications, and how we can make them work together. So for that, we need to speak about back pressure and about reactive streams. And I will do two demos, one at the beginning to show you what the problem I'm trying to solve, and at the end, hopefully solving the problem. So spark streaming, just to make sure, does everybody knows how spark streaming is working? Anybody doesn't know how spark streaming is working? Okay, well, that's good. So we can go fast. So spark streaming is based on mini batch, and the basic idea is during every interval, data is received, and at the end of the interval, a normal Spark job is run on the data which is received. That's really only that. You can use all the tools that Spark are providing, plus extra functions that are specific to Spark streaming. So now that we know about Spark streaming, let's move to reactive applications. So reactive application is something that us at Lightband plus other companies created a few years back to describe what we think should be a good, modern, scalable, resilient application. It has four characteristics. It has to be elastic, responsive, resilient, and message-driven. So you can get all the information on the website. I will just give a few more words on each of the parts. So responsive, it means that you need to respond to your client's request in a timely manner, even if the service is degraded. Resilient means that you need to stay responsive when there is any failure. Elastic, it's to be able to stay responsive again. I shouldn't use responsive every time. To stay responsive under the load, both if the load increase and the load decrease, so you can reduce the size of your cluster as needed. And everything is message-driven, so all the communication are done by message passing. So this is the Lightband Reactive platform. This is what the project we are working on. So Akka is an actor system, which is the base of all our products, so an actor system is something that sends messages between microprocesses. And on top of that, we provide Play and Lagom, which are a web application development system, and Lagom is a microservice development system. And we also do support for Spark. And okay, so yeah. So how is Spark looking in terms of being a reactive application? So the resilience in Spark is really, really good. You know that there is no problem. You don't lose any data if a node dies and things like that. Specifically for Spark streaming, there is extra support which was added to make sure that you don't lose any data and you process everything correctly. So the specific point I will look at today is what is happening if you have excess volume of data. So as I was saying before on Spark streaming, every interval you receive some data that you process at the end of the interval. The problem is if you receive too much data that you cannot process during the next interval, the data that you receive in the next interval should be processed at the end of the interval, but you're still processing the data from the previous interval. That's a lot of intervals. So you start to delay. You want to process interval 2, but interval 1 is not finished, so you need to wait to be able to process interval 2, and so on and so on. So I will just show you what's happening in Spark streaming if you get into this problem. So I have a small application which has three main parts. So there is an random number generator which I can tweak to send more or less messages. There's an application which is a reactive application written in Spark streaming. In ICAStream, different streaming in ICAStream, which is doing some computation with a random number to generate some values of pi, and then I send all those values to Spark streaming to do some statistical analysis of is the value of pi I get is good or bad. The value is bad in my test. To run my demo, I will do it on my nice small Raspberry Pi cluster. The main reason is I like to do it on real hardware, and usually it's kind of hard to connect to cloud system from a conference, so I have my own little cluster. So in my cluster, I'm running one play application, which is, I can show you, where is it? One play application which gives me some information about what's going on, why is it not running? It should be running, something broke. Okay, let's restart the thing. Okay, I lost network. That's not good. Let's try to get network back. I mean, I could run it on my machine, but it's not as fun. Okay, I have network back. I get my connection back. Okay, I need to restart. It takes 2 seconds to restart. So, for some reason I lost my connection, so it takes some time to start to send data to the system, and we need to wait for Spark streaming to start. Come on, faster. There we go, we started. So I'm generating some values of pi, which, as I said, is not a good way to generate values of pi. So what I have in this page is a number of requests that I ask the random number generator to generate every second. The actual rate of number that the random generator is generated. The number of elements which are received by my Spark streaming job. Is it a bit? No. Everybody can see at the bottom. It's fine. And the time it takes to execute. So right now I'm just sending 10 message second, which is not really fast. So let's go for 1,000 message. We can switch to the Spark streaming UI to see what's happening. So I had almost no message to start with. I went to 1,000, no, 3,000 message per second at the Spark streaming level, and my processing time went a bit up, which is fine. So let's make it do more work. So let's double the number of elements. So I asked for 2,000 elements, and I do generate 2,000 elements. Because I'm sending more data, my value of pi is getting better and better. And the execution time is still, so my Spark streaming job is set up to run with a 1 second interval. So right now my execution time is just under 1 second. So everything is still fine. So let's put more data. So 4,000 elements per second. And the random number generator should be stabilizing at some point. Yeah, it's stable more or less. So I'm receiving a lot of records. So for amount of record in Spark, I mean, those are Raspberry Pis. They are not really powerful. And the execution time is more than 1 second, which means that it takes too much time to process. And if I look at the graph at Spark streaming, you can see the scheduling delay, which is the time it takes between the end of the interval and when the computation for the value of the interval is starting is going up pretty fast. So let's see, what do we have right now? So I have computation of 1 second, and basically every result is already arriving 10 seconds too late. So it's a stupid example, that's a really simple example. If you have a real system and you have maybe like a 5 second or a minute interval, and you start to receive your data 10 times too slow or 20 times too slow, you start to get, 20 minutes too late, which start to be really bad. So that's what we want to try to fix. Let me just reset the. So one thing which is good is Spark streaming is really reliable. I could get this test to run way further, and then I will start to fill up the memory of Spark, and they will start to need to cache data on disk, and get even slower and slower, and at some point we just stop. But Spark streaming never die. It just stops at some point, and it will recover by itself, but you will lose some data, and it will be really bad. So let's see. So I asked it to, I stopped to sending a lot of data, but it's still processing the backlog of data. So it's, if you get to this state, even if it's not for a long time, it takes some time to recover. It will recover at some point. Come on. Or if somebody can make a Spark streaming page that refresh automatically, that would be sweet. Okay. So you see it starts to recover. It's at the end of the scheduling delay is going down and everything. So we'll reset the test for the next part. Okay, let's get back to the slides. So to be able to get a system that works fine and doesn't crash, what we need is back pressure. So the idea of back pressure is very simple, is that a slow customer to be able to tell the producer that you're going too fast, you're sending me data too fast. So the consumer doesn't have to accumulate data and store data to be processed. Yes, so the producer apply pressure and the customer apply back pressure to say back off. So if you remember your classes of TCP, at the TCP level, in the TCP IP protocol, there is a back pressure system. In each and every frame that are exchanged between the two parts of the connection, there is information about the side sending the frame saying that this is how much space I have in my buffers, and you cannot send me more data than this buffer. And if you fill up the buffers, you start to get some very fun exception in Java, something that you usually don't see at all, which is kind of really interesting. So back pressure in Spark streaming. I'm going to go fast on this one. So 1.4, which is a long time ago, and maybe you should stop using it. There was no real good way to do it. You could just set a fixed value, but you had no control. You had to be really conservative on it. Just set a fixed value. If your cluster change size or whatever, the value is fixed, you cannot do anything. So 1.5, Lightband, with the help of Databricks, we implemented a dynamic rate limiter. So at the low level is every time the job for one interval is done, we estimate the rate that the job can process data in number of elements per second. We send this information to the receivers, and the receivers somehow limit the amount of elements they receive. It depends on the receiver how the limiting is done. So how the rate estimator is working is, as I said, at the end of each job, which is run in the Spark streaming job, we get information about the number of elements which has been processed, the delay to start to process those elements, and the time it took to process the elements. And the rate is really just roughly the number of elements divided by the processing delay is the full. Processing delay is the delay before we start plus the time to process. So the rate is just the number of elements divided by the time it took to process the elements, which works really well, except that if you start to accumulate delay, if you have this formula, you never resolve the delay, because you say, I can process 4,000 messages per second, but maybe at some point you were able to process only 3,000 for a few seconds, because your system got slow, you got some bad CG or something like that. GC, sorry, CG. And you have some delay. So what we implemented is something a bit smarter, which is a proportional integrated derivative algorithm, PID for short, which it's an algorithm which is made to be able to go to some limit without going too much over the limit, and if you still go over the limit, to recover and get you to the limit. This is not something new. This is not something that's even created for computer science. This is something that was used, really used a lot in cargo ships. If you have a cargo ship, if you start to turn the wheel, which is I don't know if it's called the wheel or whatever. At some point, the cargo ship will start to turn. But if you stop turning the wheel when the cargo ship starts to turn, it will turn way more than you need. So it's why you need an algorithm like that, which tells you exactly how much, in the cargo ship, how much you need to turn, when you need to stop to turn to get to the value you want. What we have in Spark since Spark 1.5 is an estimator, and estimator is for each disk stream. So if you have a Spark streaming job with multiple disk streams, it will send the right value to each disk stream. It works with all the stream receivers. It works very well with the Kafka direct input stream because we just say Kafka, this is how many elements we want, and everything else is kept in Kafka. And configuration is fairly simple. You just enable it and you give it a minimal rate. It's just needed to be able to do the computation correctly. So this is a graph of when I was doing the test to check that everything was working fine. So the top, what's happening is this is the number of elements which are going through the system. So there's a spike. It's a long spike, and you see that. So this line is the streaming interval. There's a name, I don't remember them. And you see that it takes more time than the interval to process the data, so we start to accumulate processing delay. And with the dynamic rate estimator, it still goes a bit over, because in this case I was using the basic TCP receiver, which when you get to the limit, it starts to get a bit slower. Some delay accumulates a bit, but it is resolved and eliminated. Okay. The dynamic rate limiting in Spark streaming works really well, but there is some weakness. It assumes that all your elements are processed at the same speed, and that if you get more elements, you don't. And also that if you get more elements, you don't get an exponential time to process your data. And also, if you use the basic TCP receivers, basic TCP receivers, the back pressure is pushed through the TCP channel, which is not the. It is a way to push back to send back pressure. Problem is between the connection between your producer and your receiver will likely go through a few switches and things like that, which each of them have buffers, which means that you're going to start to accumulate a lot of data in the buffers. And if your application crashes for whatever reason, this data won't be kept. It will be lost. So the Kafka receiver is a good way to make sure you don't lose any data. So we see that there is ways to manage in a reactive way in Spark when you have too much data. You can send back pressure information. I had my ACA-Stream application, which is a reactive application. So now we need to connect them together. You need to be able to get Spark to tell my other application, this is how fast you can go. So this is the job of the reactive stream. Reactive stream is a small set of interfaces which has been created only really just for that, to be able to connect systems which have flow control, which has a back pressure system. It is a really simple. So you can find all the details in reactivestream.org. It is a really simple interfaces. There's 3 real interface, and in total there's 7 methods. It's fairly to implement a version of it in your application is fairly simple to start. After it's asynchronous code and things like that, so it's always get complicated with asynchronous code. But just to get started and to create something that works in most of the cases, it's very simple to start. Yes, so the way it works in Reactive Stream is the consumer part, basically, like in TCP, send information about saying that this is how much data I can still receive. So we should have something that works. We have a reactive application, which has back pressure. We have Spark streaming, which has back pressure. And we have a way to connect them both together. So let's see it in action. And it's still running. Yay. OK, so my application is running. So I enabled, let's see if I shot. I enabled dynamic rate allocation in the Spark streaming application. So let's push more data to it. I mean, 1,000 was going fine, so we shouldn't see any difference. It just go faster. So yeah, it's still going fine. It's under the 1 second. So it's send the double amount of data. And we go to 2,000, somewhere around. Yeah, sometimes it moves a bit. It depends basically when I measure exactly the number of elements in 1 second. We're still under 1 second, so we're still fine. So let's go to the 4,000, and it's at 4,000 we are starting to see problems. So if you look at the execution time, it's still under 1 second. It's just under or just over, but not much. Scheduling delay kind of go up a bit, goes up and down a bit. It's mostly because I'm pushing the machine fairly hard, and those are Raspberry Pis, and at some point they start to forget about it. But the number of elements that are generated by my number generator is way under of what I asked to it. So my random number generator wants to push 4,000 elements per second, but because it gets information from Spark streaming that this is just how much I can process, it processes way less data. And if we look at the Spark streaming UI, processing time is over around the maximum value, and there is a bit of scheduling delay sometimes that accumulates just because the exact time it takes to process is not always the same, and I'm pushing the machine a fair amount. That's not what I wanted to do. Let's try that again. Okay, that's blinking. So yeah, so we have it working fine. So that was for Spark 1.x from Spark 1.5. In Spark 2, you can still use a normal Spark streaming with using RDDs, and there is no problem, it works the same way. So in Spark 2, you have a new streaming, which is structure streaming. And right now, there is no such support. One of the reasons being that there is no stable source API, so there's no way to create there's except from what is already in structure streaming, you cannot create new source of data. And the model of, you know that the way they implemented structure streaming is different because you may not have ticks, you don't know exactly, you don't know always exactly when the data is processed. So there's a different model, different problems, and we will have to create a new solution for it. Yep. So I just want to add something on one thing. So I didn't run it in this way in this case, but I have a different version of this application that automatically detects the random number generator that I don't have enough processing. Not enough processing available in my Spark application. So automatically, when I detect that I don't have enough processing, I restart an extra Spark slave. And then with the extra Spark slave, I can process the 4,000 elements, and it's fine. And then I can just kill one of the machine, and then the processing, the amount of power that is available in Spark streaming just go down again, and then it limits again the rate of element generated by my random number generator. So yeah, if you have any questions.
Perfect. All right, so we've got about 5 minutes left, so if you can raise your hand, if anyone wants to ask a question, I'll go ahead and bring the mic over.
Question?
Any questions? Go for it. Yeah.
Hi, I wanted, is Spark streaming 1.5 using the Reactive Stream API?
No, in fact, I have a specific receiver which is using a Reactive Stream. So in Spark 1, I don't know, since most of the beginning of Spark streaming, you're able to define your own receiver and I have my own receiver, which has just a Reactive Stream connector, and I connect to it.
Cool. Any other questions? Please raise your hand since we got people going in and out.
Right there.
Is the code for your demo available anywhere?
Not yet, but I need to push it, yes. It will be on my GitHub, which is at Skyluc, SKYLUC.
Can you tell us what's the typical use cases for reactive streaming?
Reactive Stream is really just to connect systems that has back pressure. It's really just meant for that. It's really small. Oh yeah, something I forgot to say, in fact, is Reactive Stream is becoming part of the Java standard library. In Java 9, it's part of the concurrency module, I think. Yeah, Reactive Stream is becoming a standard in Java 9.
Okay, cool. So if any other questions, just come
Yeah.
up. So we'll just go ahead and shut it down right now, right?
Okay.
Thanks very much, everybody.
Thank you.